All right, I had a request for a Kirchhoff law video, so here it is. We have a circuit on the right here, more complicated than anything we've done in class, probably more complicated than what I would give you on a test, and definitely more complicated than a homework problem that you would be expected to solve for all of the unknowns directly. But here, we're just going to set up the equations. Kirchhoff's laws are shown over here on the left. They're used for when we have multiple batteries or when our series or parallel rules fails. First, we have junction rule, which requires us to set the current in equal to the current out at all junctions because charge is conserved. Then we have the loop rule, which is kind of a modified version of our spend all of the voltage the battery gives you rule we use, with special rules for whether we add or subtract our battery voltages and our resistor voltages. We'll get to those in a minute. One of the first things you need to do in a problem like this is start to label some things. So I'm going to keep to the color coding I have over here in the rules, but first we want to label our junctions. A junction is any place where at least 3 wires come together. So I'm going to label junction 1 there at the top, junction 2 here on the left, junction 3 off on the right, junction 4 at the bottom, and right here in the middle we have junction 5. So I have successfully labeled all of my junctions. And the next thing we need to do is label our currents. So we need to pick a direction for each of our currents, and it doesn't matter if they're wrong. We'll figure out how to fix that later, but you just need to pick one. For each separate section of wire between the junctions, you need to label a current, and it doesn't matter if they even make physical sense. So in this section of wire, I'm going to label current I1, traveling down and to the left. In this next section over, I'm going to label current I2. Over here, I'm going to label current I3. And notice I have all 3 of these currents coming away from junction 1. That's not physically possible, but it doesn't matter because Kirchhoff's law is a mathematical solution, and our math will fix that for us later. I'm going to label current 4 in this section, current 5 over here coming to the left, current 6 going downward through this battery here, current 7 in this left bottom-most section, and current 8 in our bottom rightmost section. So we know all of our resistor and resistance and voltage values. The only things we don't know in this problem right at the beginning are all of the currents. There are 8 of them, so we have 8 unknown values, which means we are going to need 8 equations to solve this problem. We need one more step before we can start writing our equation, and that is to label our loops. These are not the only loops you can label, the ones I'm about to do, but I tend to find it easy to stick in these white areas outlined by the circuits. That way you don't end up with more loops than you need. So I'm going to have one loop go around this section of the triangle clockwise. I'm going to label that loop 1. I'm going to have another loop go around this section, again clockwise. Loop 3, down here in the bottom left, I'm going to go clockwise again. And I don't have to, but I'm just going to go clockwise through all of these loops, just to keep it consistent. But it does not really matter which direction I draw the loops, which direction I draw the currents. This is a lot like choosing a coordinate system on another problem. So now we're actually ready to start writing our equations. So first we have our junction equations. And for each junction equation, we are going to set the current in equal to the current out. So first, junction equation 1. There are no currents flowing into junction 1, so the current in is 0. And current 1, current 2, and current 3 all leave from junction 1, so they go on the right side of our equation, all added together. I1 plus I2 plus I3. Now we repeat this process for other junctions. At junction 2, we have current 1 coming into junction 2 and current 4 and current 7 going out. So we get I1 equals I4 plus I7. For junction 3, we have current 3 coming in, and we have currents 5 and 8 going out, I5 plus I8 on the current outside of the equation. For junction 4, we have currents 6, 7, and 8 coming into that junction. And none of our labeled currents leave that junction, so equals 0 on the I outside. Again, this is not physically possible, but it's okay, and you'll see why later. Lastly, we have junction 5, where current I2, I4, and I5 come in, and I6 goes out. So, you may think, hey, we already have 5 of our 8 equations, but it's always good to check your junction equations because usually one of them will be non-unique. That is, one of these equations will turn out to be the other 4 in disguise. So to check that, I'm going to add junction equations 1 through 4 together. So I'm going to add up all of the left-hand sides and add up all of the right-hand sides. On the left-hand sides, there's I1 from junction equation 2, I3 from junction equation 3, and I6, I7, and I8 from junction equation 4. Equals, now we're going to add up the right-hand sides. We have currents 1, 2, and 3 from junction equation 1. Currents 4 and 7 from junction equation 2. And currents 5 and 8 from junction equation 3. And nothing from junction equation 4. So, now we can cancel a few things out that are on both sides of this equation. I1, I3, I7, and I8. And what we have left after we do this is I6 equals I2 plus I4 plus I5. This is exactly the same as junction equation 5. So junction equation 5 doesn't give us any new information. We can construct it using just junctions 1 through 4. So junction equation 5 does not count as one of our equations that we need to box. It turns out you can combine any of the 4 equations and it will spit the 5th one back out at you. So it's not specifically junction equation 5 that's non-unique, but one of these equations is non-unique. Just to check, let's make sure we can't add junction equations 1 through 3 together to get junction equation 4. Maybe we have 2 non-unique equations. So adding 1 through 3 together, we have I1 plus I3 on the left side. And then on the right side, we have I1, I2, and I3 from junction equation 1. I4 and I7 from junction equation 2. And I5 and I8 from junction equation 3. If we follow the same process and cancel things out on opposite sides of the equation, we end up with 0 equals I2 plus I4 plus I7 plus I5 plus I8. So this does not match junction equation 4, so that means junction equation 4 is unique. It does give us new information. So, like you'll be expected to on the test, you need to box the equations that count towards your total, and we get 4 equations from our loop equations. Or sorry, from our junction equations. So we've got 4 of our 8 equations, and the other 4 are going to come from our loop equations. For each of our loops, the total voltage around the whole loop is 0. So for loop 1, I'm going to start off with 0 equals, and all of these equations will start with 0 equals. And if you follow my cursor over here, I'm going to make my way around this loop once, going through every circuit element, and I'm going to either add or subtract the voltages I get for each circuit element as I go. There are some rules you need to follow to determine whether you add or subtract these numbers. For batteries, you add the battery voltage if the loop goes forward through the battery. By forward, I mean the normal direction current flows through a battery, and we subtract the battery voltage if the loop goes backwards through the battery. So let me color code this if the loop goes forward or if the loop goes backwards. For resistors, it's a little different, and what matters there is whether the whether the loop direction agrees with the current direction. So if the loop and the current go the same direction through a resistor, or both going to the left, then you will subtract that resistor voltage. If the loop and the current go opposite directions through that resistor, then you will add that resistor voltage. So just to be clear, I'm going to draw a couple more examples over here because we could have both loop and current going through the left and you would still subtract that, or we could have the loop going to the left and the current going to the right and you would still add that. So I'm going to need a little bit of space here. So what was I on? This one, I think. So for my loop 1 equation, again 0 equals. And I'm going to start from the very center of this circuit as I make my loop, and the first thing I encounter is this 5 ohm resistor right here. My loop, as I work my way around, is going to the left through the 5 ohm resistor, but my labeled current I4 is going to the right. So this means my loop and my current are going opposite directions, so I need to add this resistor voltage. In resistors, you calculate their voltage with Ohm's law, so that's the current times the resistance. Which current? I4. Which resistance? 5 ohms, because that's the resistor we're talking about. If we follow our loop along, we go around the corner at the junction, and then we go through I2. Our loop moves upright through I2, but our labeled current moves down left. So the loop and the current are in opposite directions. So again, we will add this resistor voltage, plus the current times the resistance. I1, because that's what section of the circuit we're in, and 2 ohms, because that's the resistance of that resistor. Then we get to a battery in loop 1. For the battery, all that matters is the direction of the loop, not the direction of your labeled currents. Our loop goes backwards through this battery, opposite of the normal direction of current flow through a battery, so we will subtract that battery voltage, minus 10 volts. And the last thing on loop 1 is we go down through the 3 ohm resistor to get back to our starting point, and the labeled current I2 also goes down. So since the loop and the current are in the same direction, this time we will subtract our resistor voltage. Now we're back to where we started, so this is our loop 1 equation. Next, we're going to do the same thing for loop 2. Again, I'm going to start at the very center. Don't forget your 0 equals at the beginning. So the first thing this loop does is goes up through the 3 ohm resistor, but our labeled current I2 is going down, the opposite direction. So we have to add this resistor voltage, adding I2 times the 3 ohm resistance. Then our loop goes down right through the 4 ohm resistor, the same direction as I3. So since the loop and the current are in the same direction, we will subtract this resistor voltage. And lastly, loop 2 goes forward through the 8-volt battery, so we will add that battery voltage. Loop 3, again, I'm going to start at the center. The first thing we do is we work through loop 3 is go backwards through a 9-volt battery. So 0 equals backwards loop through a battery means subtract the battery voltage. And then we go through the 6 ohm resistor, the opposite direction as I7. So we will add that resistor voltage, I7 times 6 ohms. And then we go through the 5 ohm resistor, the same direction as I4. Since the loop and the current are in the same direction, we will subtract that voltage. Last but not least, loop 4, again starting at the center. First we go backwards through an 8-volt battery, 0 equals, and we make that battery voltage negative. Then we go the same direction as current 8 through the resistor, so we will subtract that resistor voltage, I8 times 7 ohms. And then we go forward through the 9-volt battery, so we will add that battery voltage. Then we're back to where we started. Just to really drive this home for our loop rule equations, for battery voltages, it is just the direction of the loop that matters. For resistor voltages, you need to compare the direction the loop travels through that circuit element with the direction your current label goes through that resistor. So there's different things to consider for battery voltages and resistor voltages in your loop rule equations. This is 4 more equations, and we needed 4 more to make it to 8 total. So here we are. Those are our 8 equations, all boxed just like you'll need to do on the test. And our number of equations that we've boxed matches our number of unknowns, which means we have exactly as many equations as we need, no more, no less. So I promised I would get to the non-physical directions for these currents. I did not solve this system of equations problem myself. If you're clever with matrices, you can do it that way, but I just plugged everything into Wolfram Alpha, and these are the numbers that it spit out at me. To the nearest thousandth on all of these, I1 is 1.655 amps. I2 is negative 2.089 amps. I3 is 0.433 amps. I4 is 0.085 amps. I5 is 0.291 amps. I6 is negative 1.713 amps. I7 is 1.571 amps. And I8 is 0.143 amps. I do not expect you to be able to do this. This is an absolutely horrid system of equations problem. If you want practice or a helpful YouTube video for solving systems of equations, the basics are in one of my essential skills videos for my 105 students, and there are plenty of system of equations practice problems online. But I want to focus on these negatives. Two of our currents are negative, I2 and I6. This doesn't mean we've screwed up. It doesn't mean we have to start over. When you get a negative value for one of your occurrents, the magnitude is correct. It just means you picked the wrong direction to begin with. So I2 is still 2.089 amps, but it actually goes up through this 3 ohm resistor instead. So no need to redo the whole problem. This just means I2 and I6 are actually in the opposite direction of my initial labels. All of our other currents came out positive, so all of our other currents are in the correct direction. So just to make that clear, my actual current directions I'm going to label on here. I1, we picked in the correct direction. I2, we picked wrong. Our number is fine, but the current actually flows up through I2. I3 was positive, so current really does flow that direction for I3. I4 and I5 were also positive, so it looks like we just happened to pick the correct direction for those currents. But I6 is negative, which means current actually flows up through this section right here, not down like I labeled it to begin with. And I7 and I8 we chose correctly the first time around. So wherever you get a negative current, it just means you picked the wrong direction to begin with. And you can still keep your magnitude. That is it for this video. Hopefully this helps with your homework and with your preparation for test 4. There's also another video on resistor circuits that I highly recommend watching before you take test 4 next Monday. But that's it for this video. Have a good day, and I will see you in class later.